So a couple of things. So M.2 is very interesting for us from the perspective that we can use it in pretty much every one of our compute and storage, and for that matter, network platforms. It's a nice, small, convenient form factor. Ultimately, its size limits the power and maximum capacity of the device, and actually that works out quite nicely in a lot of applications. In a lot of places, we don't need 20, 25 watt flash devices. We don't need 8 terabytes or 16 terabytes of flash, right? We're perfectly good with half a terabyte, 1 terabyte, even 2 terabytes. That's more than good enough. So in those cases, it's nice to be able to have a smaller form factor device that we can use in a lot of different applications. So the other benefit is of course, it's a commodity device at this point. Pretty much everyone builds one or will be building one shortly. And then second, the M.2 device is nice because we can actually scale it up. So in some cases, maybe we need more capacity or more IOPS, or perhaps more importantly, more IOPS per terabyte, for example. So in this case, you can, because of the size, we can basically add more or less devices or add different capacities, for example. And to kind of illustrate this point a little bit further, I've got a quick performance slide. So I have the caveat, it is preliminary, but it definitely shows the effect quite nicely. So let me explain this a little bit further. So the data that you guys see on here is a read while writing test. So this is intended to emulate a real world workload. So this isn't a synthetic benchmark in the sense that, like, it goes up on a marketing slide. This is intended to emulate an actual running workload. So what I'm showing here is basically at fixed read IOP levels, which is really how an application runs, right? An application doesn't use 99% or 100% of the available bandwidth or IOPS. It uses what it needs to use, right? So what we've modeled here is basically the number of different levels and then looked at what the read latency is at those different levels. Ultimately, this is an important metric for us at Facebook at least, is at a given IOPS level, what is the actual read latency? So what you can see on the left side is if you have 2 M.2s installed, and then if you were to install 4. So the blue and red bars are basically the mean and P70 read latencies. Obviously, there's not a ton of variance there, or it's kind of eclipsed by the P99 latency, of course. But you can very clearly in the P99 latency see very nice shift in terms of the reduction in terms of read latency as the same IOPS level. So that's actually a pretty big benefit, right? I mean, if you can use ultimately the same capacity but have more devices and therefore lower your outlier read latencies, that's a good thing.
Chris?
Yes.
Are these, so that you've rated two, the one on the left are 2 drives, and then you rate 4 them together, or is it?
That's correct.
By 2, okay. So
that's right. So it's 2 devices and 4 devices. Basically, yes, we just created RAID volumes out of it. Exactly. All right. So let's talk a little bit more about the design itself. All right. So in terms of design objectives, so we wanted to make a not passive, but as close to a passive design as we could make. Basically, there's no PCIe switches on this card. There's no retimers or redrivers. The PCIe connection is completely passive. So it goes from the edge connector of the card to the M.2 connector itself, and that's it. We wanted to make sure the design was future-proof, and I'll explain that in a little bit, in the sense that we want to be able to support not just existing M.2s, but also upcoming devices in the next couple of years. So I don't want to have to respin the design just because we made a relatively minor change in the M.2 itself. And finally, we want it to be a low-cost card, and to make sure that we can use it in the most amount of systems, we really want it to be PCIe chem compliant. So in this case, it's a full height, half length card. because that's really the only way to get 4 M.2s on the card at this point. And feel free to ask questions throughout, guys, but you don't have to wait to the end. So the concept of it is shown there on the right. So let's look a little more in detail. So basically, the way it works is we take the BIA16 edge connector, we map 4 lanes to each of the M.2 connectors, just straight connection, and we route it as cleanly as possible without having to cross PCIe lanes. The M.2 connector that we're proposing on this version of the design would be the M key version, and it would be a 5.8 millimeter height. The reason we picked that height is because that allows us to have space underneath as well as above the device to provide thermal pads and heat sinks. Obviously, one of the bigger trade-offs with M.2s is that it's a small form factor, so if it consumes a lot of power, your power density is very high. So thermals are certainly a challenge. There's no question about that. But we believe we have a thermal solution that will work quite well. An example of which we'll show here in a couple of minutes. But the stack height there is important because that makes sure we kind of optimize that we have space both underneath and above, so we can optimally cool NAND that's on both sides of the M.2. Yeah.
The 5.8, the D5 connector, or is it higher than the spec?
It will, yeah, no, it's higher than
the
D5. That's correct. Yeah, so for D5 you would only need a 4.2 millimeter, I believe. Sorry, go ahead.
The lane segmentation is taken care of by the BIOS?
Yes, I will get to that actually. So the other part of this is there is an ECN. So the pinout for this is the socket 3 pinout in the spec. If you're familiar with that. There was also an ECN for the M.2 spec, which added SM bus support on a couple of pins. So we definitely will have that wired up as well. Especially with the thermals of the devices, we believe that's going to be critical so that we can read temperatures directly off of the devices and implement that straight into our fan control algorithms versus trying to guess at what the temperatures might be.
Hey Chris, are you going to do a step up, step down? Is the volt change?
Yes, there will be a level shifter. Unfortunately, the spec assumes that the devices want a 1.8 volt. I would love to see PCI SIG reverse that and make it 3.3 so that we only have 1 voltage going in, but that's a whole separate conversation. All right, so mechanicals. Sorry, it's a little bit hard to read, but basically, So we're going to have a set of mounting holes for a top side thermal solution. By top, I mean top in reference to the PCIe top side. We're going to have some mounting holes for a bottom side thermal solution, and bottom in this case means the bottom side of the PCIe card itself. So the bottom side height is 2.67 millimeters, so we still have a little bit of space. It's not a lot, but we can put some there, a small enough heatsink there, and our simulation suggests that that will actually be useful. So the way that will work is we'll have a thermal pad underneath the M.2 that will connect to a copper plane that's on both sides of the PCB of the carrier card, and that will help conduct heat through the PCB, through and into the PCB for that matter, and then into that heatsink on the backside. Basically, we want to try and pull as much heat out of the M.2s themselves and into the other boards as possible.
Copper plane, is it solid? So like the solid copper plane goes over the.
It's solid on the planes that we have there. Exactly. And the plan is to basically stitch VS through it as much as possible. So vertically we conduct as much as possible. Yeah. You asked the next question. So the short answer, so we're going to provide mounting holes for 2280 length, as well as 22110. So from our perspective, basically the market seems to have been pretty much aligned to 2280 and 22110 at this point. Obviously, there's a bunch of other flavors that you could build, but at this point, it seems that people are pretty much focused on those two. There were some 2260s for a while, but those have pretty much disappeared. So in terms of device support, kind of to your question, in terms of lengths, we're going to support 80 and 110. The bottom side thickness, we're going to try and support the standard maximum of 1.5 millimeters. The top side is where it's a little bit interesting. Because of power loss protection, a lot of devices are still needing a little bit more than the standard D5, which would give us, 1.5 millimeters on the top. So to accommodate taller capacitors potentially, we're proposing right now a maximum top side thickness of 3.1. I would personally like to see that come down to somewhere closer to 2 millimeters because, it actually makes it quite difficult to account for a variance between 1.5 and 3 in the thermal pad designs. So I'm hoping we can update this in the future and just stick with 2 millimeters or so. But I need to get some more feedback from the flash suppliers to see if that's a feasible option. Okay, power consumption. So this is an interesting one. The spec itself basically limits the M.2 power at this point to 8.25 watts. However, if you look at the spec in more detail, the connector itself has more than enough pins in current carrying capacity for up to 14.85 watts. So it is not currently as part of the default spec, but when I mentioned future-proofing earlier, there's definitely benefit to having higher power M.2s as well. Certainly, most of the M.2s are power constrained, right? In a lot of cases, they're having to artificially cap the performance because they simply didn't want to exceed 8.25 watts. So our proposal is basically, well, we can make the design such that if someone wants more performance, is willing to pay that cost, why not let's build up to the maximum capable. And if you want to use something in between there, that's certainly fine, but at least we have the option to do that. So the goal is basically we will design the VR solution to be have BOM options so that you can support up to the 8.25 times 4 or up to 14.85 times 4. So you would have the option then later to pick which one of the two you want. Okay, so somebody asked about BIOS bifurcation. So good question. So the way we are implementing it, what we have on our motherboards basically is we have connected all of the present 2 pins on by16. So there's a B81, B48, if I remember correctly, B31, depending on the length. All of that is connected to the PCH, so the BIOS can read those pins. And what we're proposing as part of this is the standard presence detect for by16 requires that you connect B81 to A1, which then shows up as a 0 basically to BIOS. Our proposal is that we also add B31, just pull it down on the card. So that way the BIOS basically can detect if those 2 pins are low, it knows that there's a one of these types of cards installed. It can say, as part of BIOS enumeration, PCIe enumeration, okay, I detected this card, and we can bifurcate it to 4x4s. I can confirm this works because we already have a BIOS and a design that does this. So this way you kind of have an auto detection. You don't have to worry about changing the BIOS for a specific card being installed. Certainly that is an option if you want to do that, but at least this way we have the ability to auto detect as well. Does that answer your question? Right?
It does answer the question. So this doesn't necessarily automatically work for legacy BIOS. This is a forward-looking thing.
That's correct. It is a forward-looking thing. I would love to be able to support legacy, but it's not there. Okay, so this is just highlighting the B31 pin that we're going to use. All right, so clocks and reset. So for the PCIe clocks, we'll have a clock buffer on the card, which will fan out the reference clock from the edge connector to each of the M.2s. So we'll still maintain a common clock architecture in this. Obviously, at some point, if people support separate reference clocks, 100% across the board, and that works reliably, then this won't be needed anymore. But for now, we're going to implement the common clock. And then the same thing with resets. Since there's a single reset coming in, we just had a buffer there to fan that out to the individual M.2s. Okay.
Is the clock buffer going to be PLL mode or bypass?
Probably bypass. Although most of them are configurable, so we can make that a bond. Okay, so for the I2C or SN bus architecture, so I mentioned earlier the ECN to connect the SN bus on the M.2s. So we'll have a MUX basically, or I2C switch, whatever you want, on the card, so that the addresses of the devices on the M.2s can be the same, and then the BMC can later select which one of the M.2s it wants to talk to. We're also going to connect the SN bus alert. We have another basically reserved pin on the PCIe edge connector that we're going to use for that. Our motherboards already use this. It basically have a placeholder for this anyway. So if you want to implement the alert signal, it'll be there if you want to use it. The card itself will have an E2 PROM, so you can keep crew ID information in there, serial numbers, part numbers, product numbers, etc. The usual IPMI format. We're going to have a couple of I/O expanders, and this one specifically will drive LEDs on the front edge of the card. So if you want to have one status LED per M.2, we'll have the option to do that. And if the BMC detects, for example, that there's a failure, or the host detects there's a failure, it can light this LED. Tell a service technician which of the 4 devices is broken. And then we have another optional feature that we're going to put on here so we can test it out. We've added basically an I/O expander to do power and reset controls of the individual M.2s. Obviously, this is a little bit challenging because if you power and reset an individual M.2 while the OS is up, that basically looks like a surprise hot removal, right? So there's some software work that has to happen there to make that work nicely. But we want to implement it so we can try it out and see if we can work around it in software. Either way, we're going to have a bypass option, so they'll come up and get out a reset by default, so it's not going to impact the normal power down, power up flow. And then finally, we're going to have a power monitoring chip, which will sit basically between 12 volts and the 3.3 volt converter. So that way we can actually read the power consumption of the entire card out of band. So I mentioned the 3.3 volt VR earlier. We're going to design it such that it can do up to 18 amps. For the entire card, so that way we are future-proof for the higher power M.2s. And we'll have a BOM option to do a lower current capacity, if you want to cost reduce it. All of the other devices that are SN bus or I2C accessible are going to be powered up with 3.3 volt aux. The reason for that is that way if the system is off, the BMC still has access to those devices. So, go ahead.
A little bit unrelated, but still in regards to power,
yes.
A lot of your designs don't require PFIL or PFAT for power cut protection. Does this thing have it now, or do you require it to design?
So actually, it's somewhat independent of the spec because it really there's no additional power loss protection circuitry or hold-up capacitive on the card itself. At this point, so if basically it's up to whichever M.2 you pick. So you can do non-PLP or PLP versions. It's up to you.
What's power? What's power coming in? So
Power coming in is 12 volts.
12 volts is
Yeah.
off the bus, or you have a push connector?
Nope, everything is fed through the PCIe connector directly. That's right. That's right. So the slot here is, depending on depending on what your system limitation is. In our case, for example, they're 75 watt capable slots, so we can definitely support the higher power M.2s. Yeah.
We plan to stagger the power up so that we can control the ramp rate.
That's a good question. His question was, do we plan to stagger the power up of the M.2s just to minimize, peak inrush currents? I think that's a fair suggestion. We can definitely do that. I have to look at it in more detail, but yeah, I think we can definitely do that.
Is there a processor on board that can control that sequencing, or you guys will do it in hardware?
No, we'll do it in hardware. That's right. Well, we'll just have a fixed sequence. We'll just, assume each one comes up, 20 milliseconds later or something. Yeah, exactly. Yeah, I don't want to add any micros on here. Keep it really simple. Okay, so this is preliminary thermal data. So what you don't see in here is the heat sinks that we're using. But in the simulations that we ran, we used 14 watt M.2s, and we are able to maintain the temperatures of all the components on the M.2s to within their GK specs. So we know it is possible.
Is this test data with a heatsink and you peeled the heatsink off?
Yeah. This is just a model. It's not showing the heatsink, just to make it clear, like where the M.2s are.
What's the airflow that you get?
So actually, this was in our, we ran the simulation in our Leopard servers, and at 30% fan speed. So actually the airflow there is quite low at that fan speed. So if you have another system that has higher inlet temps, or if the card is in the back of the system, your airflow conditions will be different. So, well, we can provide a recommendation. So what I'd like to do actually is show you guys a card that the Seagate team has designed that is compliant with this spec. It'll give you a very good indication of what the heatsink, for example, could look like. So Pete, if you want to bring it up so people can see it, that would be great. So you can kind of see the top side heatsink here. So this is kind of one implementation. This one has basically 4 individual heat sinks. So you can't see it really, but the thermal pad is underneath. So we're actually in the process of testing this out and seeing how, from a thermal perspective, this will work. But things like the BIOS auto detection, the bifurcation, and so forth, all of that already works. So we know that the functionality is there. But this kind of gives you guys an idea of what we have in mind. Okay. So for more information, we'll have the spec published shortly. Let's see, I was going to say, I don't know if we have another one in the Facebook booth, but we have another early prototype that we can show you guys. But otherwise, any other questions? Yes?
Oh, did you have a bonus estimation price?
I do, but not one that I can talk about.
Say, how do you do it?
No. It's not hundreds of dollars. Tens of dollars.
For the Seagate sample, is there a capacity that was set, or how much capacity and flash was it?
So,
Or can you set
you guys want to answer that?
3.85. Question and answer, I'm sorry, I'm new here.
So the question was how much capacity was on the Seagate sample, and the answer is it's 4 960 gigabytes, so 3.85.
With OP of what?
7%,
7.
960 gig.
960 per M.2 times 4.
And there was a question about power loss data protection. You have that on the M.2.
Yeah.
Yes.
What about it?
We do have power loss data protection.
One more question is to the performance. You guys talking about is that a software rate? Is it RAID 0 you're talking about when you're talking about?
Yes, in that specific set of test data, yes, that's correct. It was software. Any other questions, guys?
Is that going to be on shareable? I see you're
Yes,
recording them too.
the slides will get posted, and like I said, we'll be able to post the spec shortly. If you guys have any other questions, come find me.